Mr. Chairman, good morning, ladies and gentlemen. I'm happy to have the opportunity to present to you the research work we have done on the next generation train. The German Aerospace Center might be known to a lot of people of you as an entity, governmental entity, dealing with the Space Control Center for the European Space Organization, and as well supporting Airbus with new technologies and innovations. And much less known is that we are also working on transport issues for cars and for railways also, and have energy research and for some years now for security research as well. We have 7,000 employees in 32 research institutes at 9 locations in Germany. We have some branch offices worldwide and mainly supporting the manufacturing industry and operators with new technology, as already said. And this specific project, 11 institutes of our organization are involved. 3 of them are really dedicated to transport, program directorate, and the others are space and aeronautic institutes, so bringing in the experience from space and aeronautics to the development of innovative trains. Our vision is a high-speed train that is reducing the overall travel time for passengers, increasing passenger comfort, and improve environment-friendly operation. So that is what the transport mode railway is all the time, but we are in competition, especially in Europe, for cars, and therefore we try to make the trains more attractive for passengers and get them back, so to say, from the cars to the trains. And there we have something to do. We cannot run the railway in the state we have from the empire. The topics are to increase the certified train speed to 400 kilometers per hour. That is nothing new at time, but it was new when we created the project in 2006. What is the challenge is halving the specific energy consumption compared to the ICE3 train, that is the Velaro now, at 300 kilometers per hour. Specific means per seat. Reducing the noise of the train inside and outside, increasing the passenger comfort, the ride comfort, and also air conditioning. Improve the driving safety, reduce wear and life cycle cost to pay for the innovations. Cost-efficient design by modularization and systems integration, and last not least, increase efficiency of development and the permission process. Because as you might know, especially the permission process in Europe is known as very complicated, and you have to do it country by country, and that we try to overcome, or we as a research organization try to support this process. What is the result? For operators, we are increasing speed, the operation speed, and for the passengers reducing travel time. That means compared or looking on our reference line Paris-Vienna, that is 1,150 kilometers, one main line of the Trans-European network. The driving time at time is 16 hours. The flight time is with check-in 2 hours 45, and the car drive take you 12 hours about crossing the motorways. The situation with a new build high-speed line and 6 stops in between will reduce the driving time of the train to 3 hours 47, that is 67% less than it is at the moment. And even if we do not build a new high-speed line, because we have to cover a lot of infrastructure costs and do what is already decided in Europe to improve the lines as they are and make some improvements, some parts are new build, then we can use the existing lines. With 6 stops, we get down the driving time by 53%, means a train from Paris to Vienna is running 5 hours, 14 minutes. So that is attractive for the business people to travel by train, especially if they are wanting to step out of the train or enter the train in between, because the flight you cannot enter and leave in between. You can work when you are sitting on board. You can use your laptop, your handy, everything. And to feed this main line, to get benefit on the ticket sales, we have to transport people also from the wider area to the high-speed line, and that is done by a feeder train which is running 230 kilometers. So we are not looking on one specific vehicle or one specific line or something specific. We are looking on the complete system and made a solution for a complete system, because the passenger wants to travel from A to B, from his home to somewhere and back. And so we have to provide a solution for that and not tell him, okay, we have a main station and you have to look how to come there and how to get rid of your car. So we are looking on different type of vehicle. We started in 2007 with the ultra-high-speed train running 400 kilometers, and as I said, creating a feeder train or intercity train, also double deck, which is running 230 kilometers on top speed. And now we will transfer our experience to an ultra-high-speed freight train to do parcel services within Europe and can run mixed services on high-speed lines to better utilize this investment. The basic data of the high-speed train are the operating area is worldwide, because the market in Germany is not so large. On the other hand, we respect the European maximum clearance called G2 and have a standard gauge. The performance of the train is 83,000 kilometers per month. That is summing up to about 1 million kilometers per year, because otherwise we have too high maintenance costs. At high speed, the train will consume 18 megawatts, and that at 460 kilometers with some headwind and downslope. That is not so much because we can recuperate when the train is braking, so not all this energy is just consumed and lost, so to say. The operating speed is 400 service braking distance from 440 kilometers, with backwind is 8 kilometers. Full train set is consisting of 2 half trains, each 202 meter length. That's because the normal platform length in Europe for long distance trains is 400 meter. And we can seat 800 people, 40 people in first class or first comfort class, and 60% in second comfort class. Because of the clearance, we have to create the first class seats in the upper deck and the second class decks seats in the lower level. The vehicle concept is a single trailer running on mechatronic single wheels, That means we can move each and every wheel around the vertical axis by 3 degrees. So we are running active into curves to reduce wear and noise. The platform height is, according to standards, 600 millimeters, and the second level 2,600 millimeters. That makes clear that we are entering the train on both levels. We have no stairs inside the train, so handicapped persons can enter the train on both levels and go through. Go through means we can pass on the lower level as well, because we have single wheels, so the people can pass between the wheels. There is no axle. So the train is 200 meters long. We are dealing with several aspects, and I can only highlight some today. The train is running without catenary. We will have inductive energy supply. The car body has a special construction principle. I will highlight it later. We have investigated the passenger flow, and that lead to a solution where we can exchange passengers at every station within 2 minutes. We have virtual coupling. That means we do not mechanical couple 2 trains, but 2 trains are running electronically coupled each after the other. That's, so to say, making extreme flexible block. And each optical or vertical coupled train is running as one train for the signaling system. What we want to do in the future is to couple and decouple trains on the fly while driving. What speed and how to do that is subject of investigations. So, and these are the other features we are investigating. We are separating the people from the baggage. The baggage is handled like on a flight. You give the baggage away in the parking area or the station, and it will be handled automatically by machines. The baggage is inside the head of the train and is sorted there, and according to the station where you want to leave the train, and it's handed out back in the parking area or the station. I said already we are dealing with single wheel sets, and on the end cars single wheel sets. We have actively damped wheels, maybe. Braking is mainly cooperative, and we are using aerodynamical brakes when necessary. For a high-speed train, it's sufficient to brake with running resistance and recuperative brakes for the service braking, and only for emergency braking we are using eddy current brakes as well. So there are some more features I skip because of the time. The conventional passenger flow in the train at the moment is for the passengers something like catastrophic, especially when you have baggage because your train is stopping at an airport. So you handle 20 kilo to 30 kilo baggage, and people are entering the train on one side in opposite direction. So they meet in the middle of the car searching for the reserved seats, and that's a problem. There's not enough space to pass and to put the baggage somewhere. So we have some improvements now on the new trains, but it's not finally solved. We have a program from the aircraft activities handling the passengers on an A380 Airbus, and we have used that for calculating this train, and the result is a Spanish solution where we can handle 50% passenger change in 90 seconds. As I said, without the baggage, but all passengers in 2 levels. And the solution is to do the passenger passing diagonal through the car levels. So the entering on one side and leaving the train on the other side. That means you have two platforms, separating the stream of passengers leaving the station and from the passenger stream coming to the station. And that has to be because we have 1,600 passengers in a fully seated train. 800 are leaving the train and 800 are entering the train. So we have to handle 1,600 passengers in 90 seconds. If it took longer or much longer, then it makes no sense to run a fast train. We have to increase on high-speed lines also the throughput on the station, and the throughput on the station you only can increase when you are taking care of the passenger flow and give enough room for the passengers. So that's why we say you cannot separate the car construction from the station, and it is very difficult to have innovative trains on existing stations as in Europe. The development of our lightweight cars is this way. We are starting with the parameter-controlled CAD model of the body, then choosing from several body types the car type, and from that doing a finite elements model for construction and topology optimization. And the result of the topology optimization is giving you the structure of the load flow and moments, and all what you see as a skeleton is where you have to put material. And starting on with this, we do a concept construction which might be different depending on the material you are using, and the material you use is depending on what loads and what specific moments you got at a module of your car. And you can also build different modules in one car depending on the specific loads in this area of the car. So the structure is then completed, the thickness is optimized and the dimensioning is optimized and the crash areas are optimized especially here on this model, and then you have the paneling and the detail optimization for completing the car. This special configuration we used for the gear module or running gear module, and that is the second one seen here. Outside we have the door modules. All door modules are symmetric around the vertical axis, as well as the running gear modules and the passenger module. So the whole car is symmetric around the vertical axis, and you have no problem when the train is running in a different order into the station. It's just a matter of the electronics to show where the seats are and what car numbers you have. So it's no mechanical problem any longer, it's only the information system. Also, the running gears are fully covered for noise reduction. The passenger module in the running gear module is a car body and frame like honeycomb and pipe system from aluminium, and the passenger module is a fiber-intensive segment from reinforced sandwich infill. And both are fitted together and are in total reduced by 30% compared to an existing car. With these light cars, you have a problem with crosswind, and we have problems on the tunnel sections with the head wave. So we have built a unique device in Göttingen to deal with the tunnel pass and the crosswind. So here you see in front the plexi is the tunnel, to simulate tunnel portals, to control the airflow in the tunnel, and reduce the pressure wave going down the tunnel and doing harm to the tunnel construction and also when coming back to the train. And in the background, the dark gray one is the crosswind simulator. We can shoot the train with 400 kilometers per hour through the tunnel and through the crosswind section. And at the end, we have a device to catch the train. I said already we are looking into inductive power supply. Inductive power supply is nothing new. You can get it from your toothbrush and from cooking. And in Europe we are looking also to use it for electric cars and buses. And we have already had one test for a tram running 80 kilometers per hour. So in principle it works. The system has no technical limitation. The limitation at the moment is finances for the electronic devices you need alongside the truck. But we think we can reduce this number of devices and therefore the costs. And when you imagine that such a system is rolled out worldwide, the number of devices are increasing and the prices are going down. Interesting is this system, especially for countries in Northern Europe where they have problems with ice in wintertime. And we think also it's solving the problem with sand on the power lines in the southern countries. The passenger comfort is improved by 25% compared to the existing ICE train. It's calculated here. All positions in the double-deck car are 20% better in ride comfort compared to a conventional bogie. And the construction mock-up of the single wheel, single running gear we showed already on the InnoTrans 2012, and we will do further investigation to go much more in detail and have a more detailed construction. We have displayed the car body construction principle and the wheel. So you see here the fiber composite intensive segment from the passenger module. It's here part of a so-called standard room, and this standard room is now a laboratory to investigate air conditioning devices and looking into throughput of vibration and noise. We have done already the first investigations with people in autumn last year. The gear construction is shown here. That's force flow optimized chassis. Both parts are result of the topology optimization, the new principle. We have a mechatronic wheel set shown here, and we have a crash nose, or the nose is part of the element because we have no of the crash concept, because we have no mechanical coupling anymore, but have virtual coupling, so we can use the total nose as a crash element to have, in case of the standard crash according UIC, only to exchange the nose of the train, hopefully. We have, for air conditioning, a new principle under investigation, which is using infrared heating, and we have also in brand new technology for cooling the train. that is under investigation now, and we are using this generic laboratory, as said, to do these investigations. In the next, I will show you a video animation what the designers are thinking about the train. They are using our CAD data, and you will see the train running into a station with 2 levels. This is a concept now and artist's impression, but we have done investigations on the station concept meanwhile. Also, you can see the ramp to the level 2, and this is inside. On the lower level you have some loggers for the luggage of the people going to the restaurant. You have only small, whenever a possibility to put small items in the head racks, and normally you have to put everything behind your knees underneath the seat to be ready for any emergency braking, and no items, or more or less no items, should fly around inside the train. This is the upper side for the first class. So the main difference is that you have green colors downstairs in the second class, and the walnut design in the first class, and more comfortable space. Yeah. So this is a short overview about the project, and we are not building the train. Our duty is to develop technologies to make it fit to be transferred to the manufacturers, and to give operators ideas what they can request the manufacturers to deliver or put in their requirement specifications. They reduce the travel time of the train, as the concept is now, is about 50% reduced. It's passenger friendly. We can seat more than 30% more passengers per train. That is because the train is running cross-border, and if there is an opportunity to travel, we are creating some more travel, and that is calculated by us to be 27% within the country, and if you are going cross-border, it's 35%. The train is quiet. We are measuring in our wind tunnels all the high-speed trains available you can buy worldwide. So there we can measure some noise, but we have here the problem: we cannot measure the noise at the moment because it's absolutely seamless outside. And that means from our medical department we can create the next problem, that we have to generate noise so that the passenger has a feeling he's running on a train, same as with electric cars sometimes, where we have to simulate the motor. The vibration is reduced by 25%. Energy efficiency is less than 50% of the energy demand of the reference train, and the lightweight concept will reduce the body weight by 30%. So that's the short overview. I thank you for your attention.